In the early years of atomic science, the atom appeared almost solved, at least on the surface. Scientists believed they were closing in on the ultimate structure of matter. Electrons had been identified as tiny, negatively charged particles orbiting a compact nucleus. Protons, carrying positive charge, were known to reside inside that nucleus. This picture seemed elegant and complete, yet beneath its simplicity lay a deep and troubling inconsistency. When researchers carefully measured atomic masses, they discovered that atoms were far heavier than could be explained by protons and electrons alone. Something was missing, and for years, that missing piece remained hidden in plain sight. The problem was not a small one. According to the known rules of physics at the time, a nucleus packed with positively charged protons should be violently unstable. Like charges repel, and protons should push each other apart with enormous force. Yet atoms existed. Matter was stable. The nucleus, incredibly small and dense, held together against all expectations. Early physicists proposed imaginative but incorrect explanations, including the idea that electrons were trapped inside the nucleus to neutralize the repulsion. This assumption, although clever, introduced even more contradictions, clashing with emerging ideas in quantum mechanics. The deeper scientists looked, the clearer it became that their understanding of the nucleus was incomplete. This period of uncertainty was not marked by sudden breakthroughs, but by frustration, debate, and slow refinement of ideas. Experiments grew more precise, and theories grew more strained. Every attempt to force the atom into the existing framework made the gaps more obvious. Atomic mass measurements consistently pointed to extra weight with no apparent source. The nucleus seemed to contain something heavy, something neutral, something invisible to electric measurements. Yet because scientific instruments were primarily designed to detect charged particles, this neutral presence remained elusive. The turning point came not through a single dramatic observation, but through persistence and intellectual courage. James Chadwick, working in the early 1930s, approached the problem with fresh skepticism toward established assumptions. Rather than trying to fit experimental results into existing models, he allowed the data to guide him, even when it suggested something entirely new. Experiments involving the bombardment of light elements with radiation revealed strange emissions that behaved unlike known particles. These emissions had enough energy to knock protons out of other atoms, yet they carried no charge. This behavior could not be explained by gamma rays alone, as many initially believed. Chadwick carefully analyzed these results and reached a radical conclusion. The emissions were not light or energy waves, but particles. Massive particles, neutral particles. In recognizing this, he uncovered the neutron, a fundamental building block of matter that had been shaping reality long before humanity had the tools to detect it. This was not merely the discovery of a new particle. It was the correction of a flawed world view. The atom was no longer a simple assembly of protons and electrons. It was something deeper, more balanced, and more subtle. The impact of this discovery was immediate and profound. Suddenly, the mystery of atomic mass made sense. The extra weight inside the nucleus was accounted for. The stability of the nucleus could be reimagined. Neutrons provided strong nuclear attraction without adding electric repulsion, acting as a binding agent that allowed protons to coexist peacefully at unimaginably close distances. The neutron transformed the nucleus from an unstable paradox into a coherent structure governed by new forces and principles. Yet the significance of the neutron's discovery extended beyond solving technical problems. It reshaped how scientists understood knowledge itself. For decades, the neutron had been there, silently influencing every atom, every molecule, every piece of matter. Its invisibility was not due to insignificance, but to limitation in human perception and technology. This realization humbled the scientific community. It revealed that reality does not always announce its most important components loudly. Sometimes the most crucial elements are the hardest to see. The discovery also marked a shift in scientific thinking from simplicity toward complexity. The atom was no longer the indivisible unit once imagined by ancient philosophers, nor was it a neat solar system of electrons and protons. It was a dynamic, force-driven structure governed by interactions that defied classical intuition. The neutron introduced a new layer of the subatomic world, one that demanded entirely new theories to explain how particles behave when they are unimaginably close together. This moment in history also demonstrated the power of indirect evidence. The neutron was not seen directly at first. It was inferred through its effects, through what it did to other particles and nuclei. This method of discovery would later become central to modern physics, from neutrinos to dark matter. The neutron taught scientists that absence of charge does not mean absence of influence. It can mean deeper penetration, greater subtlety, and wider reach. The quiet nature of the neutron's discovery stands in contrast to its consequences. Within a few years, nuclear physics advanced at a pace never seen before. New elements were created, isotopes were classified, reactions inside stars began to make sense. The neutron became the key that unlocked nuclear energy, both constructive and destructive. But at its core, the first keynote of the neutron's story remains rooted in a simple truth. The universe often hides its most important answers behind assumptions we are too comfortable to question. Looking back, the discovery of the neutron feels almost inevitable, yet at the time it required a willingness to accept that the atom, the foundation of matter, was still largely unknown. It required scientists to admit that their tools, their equations, and even their imagination had limits. The neutron emerged not as a dramatic flash of light, but as a quiet correction, a subtle presence that brought balance to chaos. This is what makes the neutron's hidden story so powerful. It reminds us that progress in knowledge is not always driven by grand visions, but by careful listening to what reality is trying to say. The neutron did not force its way into science. It waited patiently until humanity was ready to notice it. And when it was finally acknowledged, it changed our understanding of matter forever, revealing that the heart of the atom was not just charged and energetic, but also neutral, stable, and profoundly essential. Once the neutron was recognized as a real and fundamental component of the atom, a deeper question immediately followed. What exactly does it do inside the nucleus, and why does its presence matter so profoundly? The answer to this question reshaped the understanding of matter at its most basic level. Before the neutron, the nucleus was a place of contradiction. It was small, dense, and powerful, yet according to classical physics, it should not have existed at all. The repulsive force between positively charged protons should have torn it apart instantly. The neutron did not simply solve this puzzle. It revealed an entirely new kind of balance operating at the heart of nature. Inside the nucleus, space is unimaginably tight. Protons are packed together at distances far smaller than anything encountered in ordinary matter. At these scales, the familiar forces of everyday experience no longer dominate. Gravity is far too weak to matter, and electromagnetism becomes a source of conflict rather than stability. This is where the neutron's true importance emerges. Although electrically neutral, the neutron participates fully in the strong nuclear force, a force powerful enough to overcome the repulsion between protons. By sitting between them, neutrons act as stabilizing partners, allowing attraction to outweigh repulsion. They are not passive fillers of space. They are active contributors to nuclear cohesion. This balance is not uniform across all atoms. Light elements, such as hydrogen and helium, require very few neutrons to remain stable. As nuclei grow larger and contain more protons, the need for neutrons increases dramatically. The neutron-to-proton ratio becomes a critical factor in determining whether an atom can exist or whether it will decay. Too few neutrons, and the nucleus cannot hold itself together. Too many, and it becomes unstable in a different way, shedding particles or energy to return to balance. In this delicate tuning, the neutron defines the identity of each element far more subtly than charge alone ever could. The idea that atoms of the same element can exist in different forms was once deeply confusing. Carbon, for example, could behave as a stable building block of life, or as a radioactive clock ticking toward decay. The difference lies entirely in the number of neutrons. These variants, known as isotopes, share the same chemical behavior because chemistry is governed by electrons. Yet their nuclear behavior can be radically different. One isotope may persist for billions of years, while another may vanish in seconds. The neutron silently determines these outcomes, shaping the lifespan and role of matter throughout the universe. This understanding transformed nuclear physics into a science of structure and balance, rather than simple counting of particles. The nucleus became a dynamic system, governed by competing forces and subtle arrangements. Neutrons contribute not only mass, but also flexibility. They allow nuclei to adjust internally, redistributing forces in ways that make stability possible. Without neutrons, the periodic table would collapse into a much smaller and simpler list, and complex matter would never arise. The presence of neutrons also explains why nuclear reactions release such extraordinary amounts of energy. When nuclei rearrange themselves, when neutrons are added or removed, the balance of forces shifts. Small changes in nuclear structure can result in large releases of energy because the strong nuclear force is so intense at short distances. This is why nuclear energy far surpasses chemical energy in scale. It is not electrons rearranging themselves, but the deep reconfiguration of protons and neutrons within the nucleus. The neutron, by enabling these configurations, becomes central to the most powerful processes known to physics. In radioactive decay, the neutron again plays a decisive role. A nucleus with an unstable balance of neutrons may transform itself by converting a neutron into a proton or vice versa. These transformations are nature's way of restoring equilibrium. What appears to be random decay is, at a deeper level, a search for balance. The neutron is both a source of instability and a path to stability, depending on its number and arrangement. This dual role highlights the neutron's complexity. It is not simply a glue holding the nucleus together, but a dynamic participant in nuclear evolution. The neutron's influence extends beyond individual atoms to entire systems of matter. In dense environments, such as the cores of massive stars, neutrons dominate. Under extreme pressure, electrons and protons merge, forming neutron-rich matter. In these conditions, the familiar structure of atoms dissolves, replaced by exotic states where neutrons define the behavior of matter itself. Neutron stars stand as cosmic monuments to this principle. They are objects where neutrons are packed so tightly that they define gravity, structure, and time itself. The same particle that quietly stabilizes atoms on Earth becomes the foundation of some of the most extreme objects in the universe. Understanding the neutron's role in nuclear identity also changed how scientists approached experimentation. By adding or removing neutrons from nuclei, researchers could explore the limits of stability. They could create elements that do not exist naturally on Earth and observe how they behave. These experiments revealed patterns and rules governing nuclear structure, many of which are still being explored today. The neutron opened a pathway to studying matter not as a fixed collection of elements, but as a continuum of possibilities shaped by internal balance. This insight has practical consequences that reach into everyday life. Medical imaging and cancer treatments rely on specific isotopes whose behavior is controlled by neutron count. Industrial testing uses neutron scattering to probe materials without damaging them. Even archaeology and climate science depend on radioactive isotopes to measure time and change. In each case, the neutron determines whether an atom is useful, dangerous, stable, or fleeting. What makes the neutron's role especially striking is its invisibility in chemical life. Everything we touch, taste, and see is governed by electrons, yet the neutron decides whether the underlying atoms exist long enough to participate in chemistry at all. It operates beneath perception, beneath chemistry, beneath biology, shaping reality at a level that rarely announces itself. This hidden influence is why the neutron's story feels so profound. It teaches that stability is not always about dominance or force, but about balance and quiet cooperation. The identity of an element, often taught as a simple number of protons, is in truth a spectrum defined by neutrons. Each element exists not as a single fixed entity, but as a family of possibilities. Some members of that family are stable and abundant. Others are rare, unstable, or entirely artificial. The neutron determines which of these possibilities nature allows and which remain fleeting experiments. Through this, the neutron acts as a gatekeeper of matter's diversity. In recognizing this, science moved closer to a more complete picture of reality. The atom was no longer a static object, but a living system of forces and relationships. The neutron emerged as a central figure in that system, shaping structure, identity, and transformation. Its neutrality, once a reason for neglect, became a symbol of its power. By not participating in electrical conflict, it could mediate stronger bonds. By not defining chemistry, it could define existence itself. This second keynote of the neutron's story reveals a deeper truth about nature. Stability is not accidental. It is engineered through balance at levels far below human perception. The neutron, silent and unseen, holds the nucleus together and gives matter its enduring form. In doing so, it reminds us that the foundations of reality are often built not on what is most visible, but on what works quietly, relentlessly, and with perfect precision at the heart of the atom. Long before humans learned how to split atoms or measure particles, the universe itself was already running experiments on a scale beyond imagination. The neutron plays a central role in those experiments, linking the smallest structures of matter to the vast processes that shape stars, galaxies, and the very origins of existence. To understand this role is to see how the quiet neutrality of the neutron becomes a driving force behind the most energetic events the universe has ever known. In the earliest moments after the birth of the universe, conditions were unimaginably extreme. Temperatures were so high that atoms could not exist. Matter existed as a dense soup of fundamental particles colliding constantly. As the universe expanded and cooled, protons and neutrons began to form. Their balance during those first minutes determined the chemical future of everything that would follow. If neutrons had been slightly more unstable, or if their numbers had been drastically different, the universe might never have produced enough hydrogen and helium to form stars. The neutron's properties were finely tuned, and that tuning shaped the cosmic landscape. As the first stars ignited, neutrons again became central actors. Inside stellar cores, immense gravitational pressure forces nuclei together, triggering nuclear fusion. In these reactions, neutrons allow nuclei to grow heavier without increasing electrical repulsion too quickly. This process is essential for building elements beyond hydrogen. Without neutrons, fusion would stall almost immediately. With them, stars become factories of matter, converting simple elements into the complex ingredients required for planets and life. However, ordinary fusion inside stars can only produce elements up to a certain point. To create heavier elements like gold, platinum, and uranium, the universe requires environments rich in free neutrons. These environments are rare and violent. Supernova explosions flood surrounding space with neutrons, allowing nuclei to rapidly capture them before they decay. This rapid neutron capture process builds heavy nuclei in fractions of a second. Every atom of gold on Earth carries the signature of such a catastrophic event, forged in a moment of stellar death where neutrons ruled the physics of creation. Even more extreme are neutron-star collisions. Neutron stars are the collapsed cores of massive stars, objects so dense that atomic structure no longer exists in a familiar form. In these stars, neutrons are packed together so tightly that they dominate all behavior. When two neutron stars collide, they unleash torrents of neutrons into space, creating conditions unmatched anywhere else in the universe. These collisions are now understood to be major sources of the heaviest elements. The neutron, once a quiet stabilizer inside atoms, becomes the architect of cosmic diversity on a galactic scale. Energy production is another domain where the neutron's influence is profound. In stars, energy is released when nuclear reactions rearrange protons and neutrons into more stable configurations. The small difference in mass between initial and final nuclei is converted into energy according to the principles of relativity. This energy is what makes stars shine and provides the warmth that allows life to exist. At the heart of every sunrise lies a process governed by neutron behavior deep inside stellar cores. On Earth, humans learned to harness similar principles through nuclear fission. When a neutron enters a heavy nucleus, such as uranium, it can destabilize the nucleus, causing it to split. This splitting releases additional neutrons and vast amounts of energy. Controlled carefully, this process provides electricity to millions of people. Uncontrolled, it becomes one of the most destructive forces ever created. In both cases, the neutron is the trigger. Its lack of charge allows it to penetrate nuclei easily, initiating reactions that charged particles could never start so efficiently. Beyond energy and element formation, neutrons also shape the evolution of the universe through their role in time itself. Certain isotopes decay at predictable rates determined by neutron imbalance. These decays act as cosmic clocks. By measuring the ratios of isotopes in rocks, meteorites, and ancient remains, scientists can reconstruct timelines spanning billions of years. The age of Earth, the history of climate change, and the chronology of life are all read through neutron-governed decay processes. The neutron thus becomes a historian of the cosmos, recording the passage of time in atomic transformations. In extreme cosmic environments, neutrons challenge the boundaries of known physics. Inside neutron stars, gravity compresses matter to densities so high that even the behavior of neutrons becomes uncertain. They may form exotic states of matter, unlike anything seen on Earth. Studying these objects allows scientists to test theories of gravity, quantum mechanics, and nuclear forces under conditions that cannot be replicated in laboratories. The neutron, once studied to understand atoms, now serves as a probe into the deepest laws governing reality. What makes the neutron's cosmic role especially striking is its universality. The same particle that helps bind the nucleus of a carbon atom in a human cell also determines the fate of stars and galaxies. There is no separation between the physics of the very small and the physics of the very large. Neutrons bridge that gap, reminding us that the universe operates on consistent principles across all scales. The atom and the cosmos are not separate stories, but chapters of the same narrative written in different sizes. The neutron's neutrality is key to this universality. Because it carries no electric charge, it interacts differently with matter and radiation. It can move freely in environments where charged particles are trapped or repelled. This allows neutrons to drive reactions in dense stellar cores, initiate nuclear processes on Earth, and escape violent cosmic events to seed space with new possibilities. Neutrality, often mistaken for weakness, becomes the source of its extraordinary reach. Even life itself is tied to this story. The elements essential to biology, from carbon and oxygen to iron and phosphorus, were shaped by neutron-driven processes in stars long before Earth existed. The calcium in bones, the iron in blood, and the iodine in cells are all products of stellar evolution governed by neutron behavior. Life is not merely compatible with the neutron's story, it is a direct consequence of it. As science continues to advance, the neutron remains at the frontier of discovery. Observations of gravitational waves from neutron star mergers, measurements of neutrino emissions from supernova, and experiments probing neutron behavior under extreme conditions all deepen our understanding of the universe. Each discovery reinforces the same lesson. The neutron is not a minor detail in atomic structure, but a central player in cosmic evolution. The third keynote of the neutron's hidden story reveals a profound unity in nature. The same rules that govern the heart of the atom also govern the birth of stars and the creation of elements. The neutron stands at this intersection, quietly shaping energy, matter, and time across the universe. From the first moments after the universe began to the processes that sustain life today, the neutron has been there, unseen but indispensable, writing the story of existence one nucleus at a time. Even after decades of research, the neutron has not faded into the background of scientific importance. Instead, it has become more relevant with time, quietly influencing modern technology, medicine, and some of the most advanced questions humanity is asking about reality. What once seemed like a solved particle, neatly placed inside the nucleus, has evolved into a central tool and mystery in contemporary science. The neutron's story did not end with its discovery or with the early breakthroughs of nuclear physics. In many ways, that was only the beginning. One of the most significant modern roles of the neutron lies in medicine. Certain isotopes, defined entirely by their neutron count, are indispensable in diagnosing and treating disease. In medical imaging, radioactive isotopes emit radiation at predictable rates, allowing doctors to visualize internal organs, detect tumors, and monitor biological processes in real time. These isotopes behave chemically like stable atoms, integrating naturally into the body, yet their neutron imbalance makes them visible to instruments. This delicate balance between familiarity and instability is a gift of the neutron. Without it, much of modern diagnostic medicine would simply not exist. Cancer treatment provides another powerful example. In some therapies, neutrons themselves are used to damage cancer cells more effectively than conventional radiation. Because neutrons interact differently with biological tissue, they can target tumors that resist other forms of treatment. This application turns a fundamental particle into a precise medical instrument, capable of saving lives through principles discovered in atomic physics. The neutron, once hidden deep inside matter, now directly shapes human health and survival. In industry and engineering, neutrons offer a unique way to see inside solid objects without destroying them. Neutron imaging and scattering techniques allow scientists to study the internal structure of materials, from airplane components to ancient artifacts. Unlike X-rays, neutrons are sensitive to light elements such as hydrogen, making them invaluable for examining water movement, fuel cells, and biological materials. This ability to reveal the invisible has made neutrons essential to developing stronger materials, more efficient energy systems, and safer technologies. Energy production remains one of the neutron's most visible legacies. Nuclear reactors rely on carefully controlled neutron behavior to sustain chain reactions. Engineers must understand neutron flow with extreme precision, adjusting conditions so that reactions remain stable and safe. Every control rod, every safety system, is designed around managing neutrons. The challenge is not simply to produce energy, but to maintain balance, reflecting the same principle that governs stability inside the nucleus itself. The neutron thus becomes both a source of power and a reminder of responsibility. At the frontier of fundamental science, neutrons continue to challenge understanding. Despite being electrically neutral, the neutron has a complex internal structure made of even smaller particles. Studying how these components behave reveals deeper layers of reality and tests the limits of current theories. Experiments measuring the neutron's lifetime, for example, aim to answer questions about the early universe and the fundamental forces that govern decay and transformation. Small discrepancies in these measurements could point to new physics beyond what is currently known. Neutrons also play a critical role in understanding gravity and space-time. Neutron stars, among the densest objects in the universe, push matter to extremes that cannot be recreated on Earth. Observing how neutrons behave under such conditions helps scientists test theories of gravity and the nature of matter itself. These observations are not abstract curiosities. They inform models of cosmic evolution and deepen understanding of how the universe behaves under its most intense conditions. In laboratories around the world, scientists use neutrons to probe quantum behavior. Because neutrons are massive yet neutral, they exhibit wave-like properties in ways that can be precisely controlled and measured. Experiments with neutron interference and diffraction provide insights into the foundations of quantum mechanics. These studies blur the line between particle and wave, reinforcing the idea that reality at its deepest level defies everyday intuition. The neutron becomes a messenger from that hidden realm, carrying information about how nature truly operates. The neutron also plays a role in environmental science and archaeology. Radioactive isotopes help trace groundwater movement, date ancient objects, and reconstruct climate history. These techniques allow scientists to look backward in time, using neutron-driven decay as a reliable clock. Through this, the neutron connects human history, geological change, and planetary evolution into a single timeline. It becomes a bridge not only between scales of size, but between past and present. What makes the neutron's modern importance especially striking is how quietly it operates. Unlike electrons, which dominate technology through electricity and electronics, neutrons rarely appear in everyday conversation. They work behind the scenes in reactors, hospitals, research facilities, and cosmic events far beyond human reach. This quiet influence mirrors the neutron's original role inside the atom: essential, stabilizing, and largely unseen. The neutron's story also carries a philosophical dimension. Its existence reminds us that neutrality does not mean insignificance. In a world often defined by extremes and opposites, the neutron demonstrates the power of balance. It neither attracts nor repels electrically, yet it binds. It does not define chemical identity, yet it defines nuclear existence. This paradox challenges simplistic ways of thinking about cause and effect, importance and visibility. As humanity looks toward the future, neutrons may play a role in new forms of energy, including fusion, where controlling neutron output remains one of the greatest challenges. Advances in neutron science could lead to cleaner energy sources, new medical treatments, and deeper insights into the fabric of the universe. Each of these possibilities builds on the same fundamental understanding that began with the realization that something neutral and unseen was missing from the atom. The neutron's continued relevance also serves as a reminder about the nature of scientific knowledge. Discoveries are not endpoints, they are openings. Each answer reveals new questions, and each tool uncovers deeper layers of complexity. The neutron was once the solution to a mass discrepancy in atomic theory. Today, it is a key to unlocking mysteries about the universe's origin, structure, and fate. In the end, the neutron matters not because it is dramatic or easily observed, but because it is foundational. It supports matter, powers stars, enables technology, and informs medicine. It connects the earliest moments of the universe to the daily functioning of modern life. Its story is a testament to the idea that the most influential forces are often those that work quietly, shaping reality from within. This final keynote of the neutron's hidden story brings everything full circle. From the stability of atoms to the advancement of civilization, from the birth of elements to the healing of disease, the neutron remains central. It is not merely a particle in a textbook, but a thread woven through the entire fabric of existence. By understanding the neutron, we do not just learn about atoms. We learn how balance, subtlety, and unseen forces govern the world we live in and the universe we seek to understand.